Hello everyone and welcome back to Math Made Easy. In the previous two lectures, we studied Newton's forward and Newton's backward interpolation methods. We learned that both methods are particularly useful when the x values are equally spaced. But what happens if our data points are not equally spaced? For example, if we have the data as is x and fx with its x values as 1, 1.5, 3, 4.5 and fx values as 2, 4, 10 and 20. Now look carefully at the x values. The differences are 1.5 minus 1 as 0.5 here, 3 minus 1.5 as 1.5 again, and this 4.5 minus 3 as 1.5. The spacing is not uniform. Therefore, we can't directly apply the standard Newton forward or Newton backward interpolation formulas. And this is where today's method becomes extremely useful. And today's topic is Newton's divided difference interpolation. And the major advantage of this method is that the x values do not need to be equally spaced here. So today we will understand the concept of divided difference, construct the divided difference table, derive the Newton divided difference interpolation formula, and develop the algorithm, followed by our numerical example. So let's just first understand why we need divided differences. In Newton forward and backward interpolation, we used finite differences as is del y, del square y or del cube y and up to so on. Now these formulas depend on the fact that the x values are equally spaced. But in divided difference interpolation, we don't require equal spacing. So instead of simply subtracting the function values, we divide the difference in function values by the difference in the corresponding x values. And this is why the method is called divided difference interpolation. So suppose we have two data points as is x0, y0, comma x1, y1. And the first divided difference becomes this function value at x0, comma x1 as this f of x1 minus f of x0 divided by x1 minus x0. Or you can simply state it as this y1 minus y0 divided by x1 minus x0. Now notice that the denominator contains the difference between the x values. Therefore, equal spacing is not required. Now suppose we have 3 points. The second divided difference becomes this function value and this x0, comma x1, comma x2 becomes this function of x1, comma x2 minus function at x0, comma x1 divided by x2 minus x0. Now notice something important here. The denominator here is x2 minus x0, not that x2 minus x1. And this is a very common mistake. Similarly, we get this function value at x0, comma x1, comma x2, comma x3 as this function value at x1, comma x2, comma x3 minus function value at x0, comma x1, comma x2 divided by x3 minus x0. And in general, we get this function value at xi up to xi plus k as function value at x of I plus 1 up to xi plus k minus function value at xi up to xi plus k minus 1 divided by x of I plus k minus xi. And this is a general divided difference recurrence formula. Now let's just understand how the table is constructed here. Suppose we have this x and fx values in the tabular form where we have this x as x0, x1, x2 and x3. And function value as function at x0, function at x1, function at x2 and function at x3. And we first need to calculate the first divided difference as this function at x0, comma x1, function at x1, comma x2 and function at x2, comma x3. And then we calculate the second divided differences as this function at x0, comma x1, comma x2 and the function value at x1, comma x2, comma x3. And finally, we calculate the value of the function at x0, comma x1, comma x2 and comma x3. And hence the table looks like this xi and the function at xi, the first divided difference, the second divided difference and the third one. And here in this x we have this x0, x1, x2 and x3, and function at x0, function at x1, function at x2, function at x3, and in divided differences we get this function at x0 comma x1, and then function at x1 comma x2, and then function at x2 comma x3. And for the second divided difference we get this function at x0 comma x1 comma x2, and function at x1 comma x2 comma x3. And for the third divided difference we get this as function at x0 comma x1 comma x2 comma x3. The top entries of each column are the coefficients we will use in the Newton interpolation polynomial. Now we can construct the interpolation formula for n plus 1 data points as we have now, this x0 comma function at x0 up to xn comma function at xn. The Newton divided difference interpolation polynomial becomes this pnx equals to function at x0 plus x minus x0 multiplied by function at x0 comma x1 plus x minus x0 into x minus x1 in function at x0 comma x1 comma x2 plus this x minus x0, this x minus x1, this x minus x2 into function at x0 comma x1 comma x2 comma x3, and plus up to so on. And in general it becomes this as pnx equals to function at x0 plus summation of function at x0 comma x1 and up to xk, where k is starting from 1 up to n, multiplied by the product of x minus xj, where j is starting from 0 up to k minus 1. And this is the Newton divided difference interpolation formula. Now just understand the structure. First term here is this fx0, and the second term contains one factor as x minus x0, and the third term contains another two factors as x minus x0 into x minus x1, and the fourth terms contain the next three factors. So each additionally term introduces one additional factor, and this makes the Newton form particularly convenient if we later receive another data points. We don't necessarily have to reconstruct the entire polynomial from the beginning. We can always extend the polynomial by adding another divided difference term. Now we have a question to estimate the value of the function at 2.5 using the Newton's divided difference interpolation method. So we have the following data here as this x values as 1, 1.5, 2.2 and 3, and the function value is 2.7, 183 and 4.4817, 9.0250 and then 20.0855. Now this is a more realistic problem because the x values are clearly unequally spaced. We have this as 1, 1.5, 2.2 and 3. So we can't directly use the Newton forward or Newton backward interpolation. So let's just construct the divided difference table here. For that we have this f function at 1, 1.5 as this 4.4817 minus 2.7183 divided by 1.5 minus 1 as 3.5268. Next is function at 1.5, 2.2 which is 9.025 minus 4.4817 divided by 2.2 minus 1.5 as a 6.4904. Now next is this function at 2.2, 3 becomes 20.0855 minus 9.0250 divided by 3 minus 2.2 which becomes 13.8256. And now comes the second divided difference where we have this function value at 1, 1.5, 2.2 as this 6.4904 minus 3.5268 divided by 2.2 minus 1 and hence gives 2.4697. Next is this function value at 1.5, 2.2, 3 as is 13.8256 minus 6.4904 divided by 3 minus 1.5, as is 4.8901. And hence the third divided difference becomes the function value at 1, 1.5, 2.2, 3, as is 4.8901 minus 2.4697 divided by 3 minus 1, and gives 1.2102. Therefore, the Newton polynomial Px becomes is 2.7183 plus 3.5268 multiplied by x minus 1 plus 2.4697 multiplied by x minus 1 into x minus 1.5 plus 1.2102 multiplied by x minus 1 into x minus 1.5 into x minus 2.2. Now putting the value of x equals to 2.5, therefore the polynomial at 2.5 becomes this 2.7183 plus 3.5268 multiplied by 1.5 plus 2.4697 multiplied by 1.5 multiplied by 1 plus 1.2102 multiplied by 1.5 multiplied by 1 and multiplied by 0.3. Now evaluating gives approximately the polynomial value at 2.5 as 13.09. Now the important point here is not just the final answer. And notice how the method worked perfectly even though the x values were unequally spaced. Now let's just summarize the algorithm in an examination friendly form. Just need to write the data points as this x0, y0 to up to x and yn, and calculating the first divided differences as this function at xi, xi plus 1, and hence calculating the higher order differences using this f function at xi up to xi plus k, and hence constructing the Newton interpolation polynomial, and after substituting the required value of x, and hence calculated the estimated value. So today we studied the Newton's divided difference interpolation method. We began by identifying the limitations of the Newton forward and backward interpolation. They are designed for equally spaced data. We then introduce the divided differences, derive the first, second and higher order divided differences, constructed the divided difference table, and obtain the Newton divided difference interpolation formula. And most importantly, we saw this method can be handled unequally spaced data points. And the key formula to remember is the Newton divided difference polynomial, that is this Pnx. And the most important advantage is unequally spaced data can be used. And with this lecture, we have now covered the Lagrange interpolation, the Newton forward interpolation, Newton backward interpolation, and the Newton divided difference interpolation. And in the next lecture, we will study the Hermite interpolation, which takes the interpolation one step further, because instead of using only the function values, we can also incorporate the derivative information at the given points. And we'll understand the Hermite interpolation concept and derive the interpolation formula, construct the required table, and solve a complete numerical example. So thank you for watching, and if you found this lecture helpful, don't forget to like, share and subscribe to Math Made Easy for the complete numerical analysis course. Keep learning, keep practicing and keep questioning, and I'll see you in the next lecture.